Well, we've seen this one before, but in a different context. This was our uh, seven, what is it, 747, some jet blowing a truck off the taxiway at San Francisco Airport, a staged demonstration, of course. And our point then was to look at Bernoulli, to look at the velocity coming out of the engine, the velocity being killed against the truck, to calculate the pressure and calculate the overturning moment. And I think it came out to be roughly right that it's a 1,500 kilogram truck or something for the dimensions we chose. And so we were using it in that context. So today we will do the third of our conservation equations. Week 6 was mass, week 7 was momentum, and today is conservation of energy. And so energy in this context is using chemical energy inside an engine to be able to expand air to work as a jet engine does, just by using chemical energy and turning it into kinetic energy, essentially. So that's what we'll do today. Not sure what these things are. Oh yeah, and so we'll do a little example about pumped energy storage. And of course, you can see, you probably know what pumped energy storage is. It's one of the big things these days for renewables is intermittency. You only get electricity when the wind blows from wind turbines and when the sun shines for PV cells. So overnight you don't. So you have to have a way of storing energy in batteries. And one large-scale method of that is pump storage. So you pump up water to a upper reservoir when electricity is cheap overnight, if you're running nuclear plants or whenever you have the excess energy, and then you run it back through the turbines in the daytime when you need it. And actually there's one, this looks like the one actually in the Alleghenies, just off the Allegheny River in northern Pennsylvania. There's one right above the Allegheny. It's a reservoir that's created at the top of a hill. I guess around here, our hilltops, and probably true for the Alleghenies as well, are roughly 2,000 feet. Valley bottoms, State College is about 1,000 feet. And so you have that elevation gain between them. And I'm not sure what I did there. Compressed air energy storage is another one. You have caverns underground. You pump them up by compressing air in them when you have energy to spare, and then you run them back, the compressed air back through turbines to be able to recover the air, just like a big geological battery. And so things like for this would be things like in northern Pennsylvania, there's there's salt deposits, and those salt deposits are made into caverns by putting a borehole down, circulating brine at the bottom, and then retreating the casing up. So you have this big cigar-shaped cavern that may be 1,000 feet tall and a couple of thousand feet deep, that is able to withstand these pressures. And of course, geothermal energy, and actually I think this is quite a nice, I'm going to just play this movie, and I'm going to...
Our Earth is a fully charged, boundless battery. Just like our sun, which is well known and understood to be an endless source of energy on which solar power depends, the Earth has a remarkably similar renewable source of energy at it.
Yeah, I'll turn that off. So geothermal energy, of course, is one potential way to be able to recover heat from the ground. Geothermal heat pumps are popular, and of course with the Ukraine crisis a couple of years ago and the potential cutoff of the Nord Stream pipeline for gas from Russia, one of the solutions for Germany was to start prompting people to use heat pumps, which are actually quite efficient in terms of heating, providing heat for houses. It actually milks the sometimes geothermal energy, if it's a geothermal heat pump, or the air energy, just like it's basically an air conditioner. And because it uses a compressor and fluids, just like an air conditioner or a fridge, it's able to scavenge the thermal energy out of the ambient air. If it's a geothermal heat pump, it scavenges the 55 degree Fahrenheit in the summertime to cool house, and it scavenges that heat in the wintertime, which is still much warmer than the air temperature, to be able to use it. A different form of geothermal energy is kind of large-scale baseload geothermal energy, where you go in and actually not very different from petroleum gas fracking, you create a network of fractures that are hot. The geothermal gradient, low geothermal gradient is something like 25 degrees centigrade per kilometer. A high one is about 50. So if you go down 4 kilometers, you could be at 200 degrees centigrade. And so one way to harvest that heat, this is a geothermal heat pump. These are just coils of tubing 6 feet down below the frost line, where the temperature probably is something like 55 degrees around here. It varies by portions of the country. And to harvest that for individual houses or developments. But this is large-scale baseload heating, where you might want to generate electricity. And so you go down and you create permeable pathways. You have water as a heat transfer fluid. Inject cold water in one hole, let it travel across your reservoir, pull it back out hot, and then use it if it's above 100 centigrade in turbines, because you can flash it. Or even if it isn't above 100 degrees centigrade, you can use what's called a binary plant, where you transfer that heat to another fluid, a fluid which maybe boils at a much lower temperature, such as isopropyl alcohol, which is 39 degrees centigrade, I think, not 100 degrees centigrade like water, transfers the power to that fluid. You flash that fluid through a closed system through a turbine, and then condense it on the other side, and then use that to be able to harvest electricity all the way down to something like 40 degrees. So that's one way of doing it. So this is another company called Evor, which is Ever, I guess they're called, as in the last part of Endeavor. And their system is a little different because it's a closed system. I'm still not sure, I believe, how it works completely. So instead of making a reservoir like this, their system is to, they're making the point that sometimes you get earthquakes from these because you get cooling of the rocks. And their system is somewhat different. I guess we're getting to it now. And what they do... Oh, I'll go back. So they have this technology where they have a closed system in the subsurface. So they don't have any fluids coming up. They drill a hole down, drill it horizontally, as they can do. You drill another one at the other side to meet it, which amazes me that you can do that, because these aren't 10 feet deep. These are probably 3,000 feet deep or 4,000, so 3,000 meter deep systems. And they then have a closed system in which they circulate some fluid. And that fluid, just like those coiled pipes at shallow depth in the early part of the picture of this movie, is a closed system that harvests heat at much deeper depths. The separation between these surface stations might be 5 kilometers, I think. And this is actually a plant that does that in the front ranges of the Rocky Mountains in Canada, near Calgary, if you know where that is. And so this is I should shut up and let you see what their technology kind of does. So you put down holes, maybe 3,000 meters deep, maybe 5 kilometers apart. You can join them on the surface if you want and circulate fluids. I'm not sure what else they're going to show, or you can have it in these radiator blades which are circulating one direction then back. So the whole deal is that you need a residence time to be able to have a large heat surface area. Basically, you need a large surface area in the subsurface to be able to get the heat by diffusion, by conduction, I guess, into the working fluid, and then that fluid carries it back to the surface. And so you can use working fluids that, when they heat up, they become buoyant, less dense. And if they're less dense, then they will tend to rise naturally by their own buoyancy. And so you don't have to provide parasitic losses by pumps to be able to recover the energy from that. So anyway, that's probably enough. But geothermal, if you can crack it, something that's been tried for 50 years, these hot dry rock projects. Certainly if you go to California, the Geysers geothermal field is about 1 gigawatt in just 50 miles north of San Francisco. But those are on plate boundaries. The west coast is the San Andreas Fault. It's a subduction zone as it goes up towards Seattle. And so those are hydrothermal systems that are already existing there, very special locations geologically around the world. And the idea for this is to be able to do this under New York City, where we're not sitting on a plate boundary, and where the geothermal gradient isn't quite so high as it is on those plate boundaries. And there isn't some natural permeability, which makes it easy to do those systems like the geysers. So that's that. I'm going to stop that there. So that's kind of the preamble for what we'll talk about today. And so this is where fluids meets thermo. This class used to be a 5-credit thermo/fluids class, and the students hated it. And so now it isn't one. Do you have fluids, thermo right after this? God, we have a lot of people here today. Jeez, what's going on? So what we've talked about, well, I'll just recap what we've talked about. So, no, I don't want that. I like. So, what did we do so far? I'm not doing a very good job. Find out how to hold my pen again. So, week 6 was conservation of mass. If you remember, we had this property which was B, which was equal to mass, and lowercase b, which went into Reynolds transport theorem, was equal to, sorry, that's not it. B was equal to B over mass, which was equal to 1. And as a result of that, we ended up with an expression was density times rate of change of volume plus volume times rate of change of density plus the sum of mass flow rates was equal to 0. And we went through a whole bunch of different flavors of static, non-deforming, moving, non-deforming, and moving and deforming. The pipe, the jet engine, and the balloon for that. Week number 7, for most of it, we were looking at conservation of momentum. V here, not volume. And so for that, our extensive property was equal to mass times velocity. Our lowercase b was equal to, again, b over m, which was equal to just velocity. And we ended up with an expression that was sum of forces was equal to, again, summations. Sum of, what was it, velocity multiplied by mass flow rate, I believe. And we did the example with the cart, if you remember. We did 3 examples, one with the JetLev, one with a cart, which had water coming in and doing this. And so what we could do is we could not only look at the velocities of the influent water, but we could also look at the forces applied on that cart. And I guess we looked at them in the horizontal direction, but we could look at them in other directions. And finally, on Friday, if you've looked at the notes already, we could take this and we could multiply both sides by r. And this becomes a rotor, which in this case, fluid coming out of the top would push it downwards against the force. And just by multiplying it by a lever arm, we get, for this, a torque, product of a force times a radius. And we can multiply that by its rotational velocity to get a work that's out of the system. So that's what we had done so far. So today, we'll talk about conservation of energy. So all of these systems have been conservative. Conserved mass, we conserved momentum. We didn't lose any momentum by frictional forces. So today we will look at energy, conservation of energy. And so for this, our B property, I'm not going to drive it other than just say it because it's some commonality, is that it is equal to mass multiplied by energy. Energy per unit mass. So this is what this lowercase e is. And if we write that out, again, lowercase b will just be mass times energy over mass, which is just energy. And what we'll find out is that we'll end up, I'm not going to derive it, but we'll end up with this expression here, which looks kind of thermodynamic-ish. But really what we'll define is just a magnitude of the energy. And energy we can define as being equal to uppercase U, this term. This is what the book uses. It's P, pressure over density, plus V squared over 2, plus G times Z. And I won't draw a figure for it because you recognize probably most of these terms. The one that you might not recognize for what we've talked about before are these first two. And we'll define this as enthalpy. And we'll call it H, because they do in the book, which is just equal to U, which I didn't define, which is internal energy per unit mass. I'll write that down. Per unit mass, because we haven't seen that before. And this is enthalpy. The two of these together is enthalpy. And you'll recognize these other terms. Actually, this is Bernoulli, pressure head. This is velocity head. This is elevation head. And we're just adding internal energy within the system. Could be chemical energy, but for us it's really heat energy within the system. And so if we throw that into this, and then we throw these into Reynolds transport theorem, which we're not going to do, we end up with this expression here. So I'm not going to do anything other than this. So you can see that these are the components. Internal energy and pressure together are enthalpy. And we define it in terms of, I guess, a control system. Control volume, I guess, right? Just as before, we have a control surface. We have a control volume. And we can look at fluxes into and out of the system, whatever these fluxes are. So enthalpy in would be this in. Enthalpy out would be this. And the summation is just over these individual terms, so which we'll define shortly. And so I'm not sure there's a whole lot more to it than just saying that we've added a term which now allows us to work with hot fluids, geothermal fluids, for instance, and to be able to say exactly what's going to happen in those systems. And this is the expression that we'll end up using. This is mass rate. This is what we've called uppercase M dot. Not sure what this is doing down here. So it's mass rate, and these are internal energy per mass. And so actually it looks a little strange, I suppose, right? So what we might do, I guess, is just make sure that we're still adding apples to apples. So what are the units of this? Pressure divided by density. The units are going to be, pressure is newtons per meter squared. Density is kilograms per meter cubed. And so the units are going to be Newton meters per kilogram. And so that's the same. A Newton meter is a joule by definition. And that's a unit of energy per mass, unit mass, right? Joules per kilogram by definition is that. It's kind of strange that it also is equal to this. I guess what we could also do is we could use the definition of a joule, or actually not a joule. What's the definition of a Newton? It's actually equal to it's force needed to give 1 kilogram an acceleration of 1 meter per second squared. So we could also throw this into here, and we'd find out that if we substitute that, we have kilograms, meters, meters cubed, divided by meters squared, kilograms, and seconds squared. And hopefully some of these cancel out. Kilograms cancel out on the top. We have meters to the 4, meters to the squared. That equals meters squared, seconds squared. So surprisingly, I think, the units for this work out in that they're equivalent. So the units of enthalpy and of pressure divided by density have to be the same as these, and they actually are. We can show that the units of this, which have to be also the same as the units for enthalpy, they are. Kilograms, either kilojoules or joules per kilogram, are actually the same as the units for v squared over 2. Kind of surprising in some respects, I think, but nonetheless. And so the other parts of this are that we can prescribe, this is thermal energy in, heat energy in. And so since we're multiplying, so this is in joules per kilogram times kilograms per second. So this is joules per second. So these have to be in joules per second. And I guess the other one would be work. I know I'm writing all over. So in the turbine, you put fluids in, it does some work on that. And if you're putting work into the system in terms of a pump, then it's positive. So positive if in, negative if out. So this would be a turbine, and this would be a pump. So in a turbine, you put some hot fluids in, and you get some work out of the system as a result of that. And you just have to use the right sign convention. And actually, the heat has the same convention. Heat in is positive, it's not a pump anymore, but heat out is negative, and so we just have to be mindful of this. And what else do I need to say about that? Yeah, nothing. That's it. So that's one form of the equation, when we have hot fluid with enthalpy coming into the system. The other equation that we'll use is a much more familiar equation, which is the one that sits above it, and that's this one here. And you'll notice that this one doesn't have any heat into it, but it's exactly the same, bless you, as we've worked with before. And it's Bernoulli's equation. I don't know why I wrote it that way. Why don't I write it properly? I'm going to write it down here. So I'm going to write it, for some reason I've written it from downstream to upstream. So let me write it. So P out, I'm going to call it P2 actually. P2 over gamma plus alpha times V, what am I doing? 1, V1 over unit weight plus V1 squared over 2G times this term alpha plus Z1 plus pump head HP equals downstream, which is P2 over unit weight plus alpha times V2 squared over 2G plus Z2 plus HL. And so we've kind of alluded to that before, and it's much easier to draw out exactly what that is. So if we have a datum where Z is equal to 0. And we have our pipe going from left to right. And that pipe has a flow coming out of it at V2, or a flow going into it at V1. Then we can start detailing those individual components. So this would be Z1 to the middle of that line, I guess. This would be Z2. We've drawn this figure before, I think. Do we have pressure as green? And we called this the hydraulic grade line, HGL. So this is P2 over gamma. This is P1 over gamma. We have velocity head, P1 and V2 squared over 2G. And V1 over 2 over 2G all squared. And we have these extra pieces here. So this is our pump head. You can imagine this being horizontal. And this is our head loss. So that's kind of pictorially what it is. So these represent the fact that the alpha values are, when we look at Bernoulli equation, we look at the velocity across a pipe as just being a straight rectangular distribution of flow rates. In reality, if you look at the velocity across a pipe, because there are forces dragging on the side, the velocity profile is parabolic, as we'll find. 0 at the edges where it's kind of stuck to the pipe, as you'd expect. And so in this case, alpha is equal to 1. In this case, alpha would be less than 1. So when you have losses, then this term is not 1, as we've used before. The reality is we'll never use it differently from 1, but that's part and parcel of this. We'll always use it as equal to 1. The other terms are that we can put energy into the system in terms of a pump head. And a pump head is defined most usefully as the pump head, which is a length, because you're adding apples to apples, is equal to the power in watts divided by flow rate. I guess we've used Q for heat flow. Mass flow rate times G is the best way to do it. Sometimes I use Q for volumetric flow rate, so mass flow rate would be Q multiplied by density. Right? Mass flow rate. And so this is physically what this is. So this is Bernoulli. We know if the pipe is constant section, then by definition, these velocity terms have to be exactly the same, right? And as a result would be the same height on this. This is the upstream and downstream pressure. So in a Bernoulli system, where this is the energy grade line, EGL, hydraulic grade line is just the sum of elevation and pressure heads, just by definition. The energy grade line is the total energy head, including the velocity head. Then if it's a pipe which is of constant cross-section, these have to be the same upstream and downstream. If the pipe is horizontal, Z1 and Z2 have to be the same upstream and downstream. And therefore, by definition, the pressure upstream and downstream have to be the same as well. So there's no pressure loss in the system. But in real pipes, what, as you could probably surmise, if you look at a real pipe, you could imagine that P1 and P2 acting in the opposite directions are not the same. And that condition is because if you look at water flowing down the pipe, it exerts a pull on the pipe, and the pipe exerts a pull on the water. So the pipe is pulling against the water, moving from left to right. And so you could just do a very quick force balance, and that would be, if this is the area, equals pi d, and if this area here was equal to L, then you could write a very simple equation from what we've done for conservation of momentum, that P1 minus P2, if they're different, multiplied by pi d is equal to 2 pi r no, it's not pi d, is it? Pi d squared upon 4, right? Is equal to pi d times tau. So tau is the shear stress that's applied on the side of this. It's a force per unit area, and I guess this is multiplied by length. So I didn't really want to draw those separately, but this is the total inner. Pi dl is just the total inner area of this cylinder, and that's acting against it, and these balance with each other. So this is the essence of the head loss. So this tau really is kind of what this will turn out to be. So we'll end up developing equations that tell us exactly from the velocity of water going down pipes or flowing around wind blades, turbines, exactly what those head losses are, and we can quantify them in some way. But that's essentially what this second expression represents. The fact that in non-ideal systems, everything we've talked about until now, today, has been ideal systems. There have been no losses within the system, and now we're starting to accommodate that as a possibility. So head loss we can define, and if we want to overcome that head loss, we have to provide some energy into the system, which is a pump head, which again is a length, because all of these are lengths as well, and we can define it. So if we know what the loss is within our system, we want to have the pump head to be equivalent to that. And so if we know how much flow we want to get in the system, we can calculate how big a pump we need in terms of its wattage. So that's kind of what we're doing. So that's it. And so I don't know why I wrote these backwards, but it's the same one, and we'll use these two expressions to be able to solve problems. Okay. Anything else? No, I don't know. So lots of math, too much math. Don't want to do that. Don't need to do that. Don't need to do that. We just need to use those two equations. And I'll just do two quick examples today to maybe cement these ideas. And so this is using that first equation, the one I labeled equation number one. And that is that it's a turbine. So fluids come into the turbine at some given velocity and some given enthalpy. Again, velocities, we might want to be aware of our units, and that is that if we use kilograms, meters, and seconds, then we'll find out that joules are always Newton meters, and watts are always in joules per second, Newton meters per second. Rate of doing work, right? This is work or energy. This is rate of doing work, which is power. And I guess the point I'm making is if you use these standard units, SI units, then you're okay in the terms of the conversions, because what we previously did was we defined that enthalpy is the same units as pressure over density. We showed ourselves that it's equal to work per mass, joules per kilogram, Newton meters per kilogram. And they have to be the same as each other because we're adding enthalpy is just internal energy and pressure. And so when we want to use this, what are we being asked? Steam enters the turbine, goes in at a velocity of 30 meters a second, and has a certain enthalpy. in kilojoules per kilogram. It's probably better to write it out as joules per kilogram times 10 to the 3 rather than do that. Comes out as a mixture of vapor and liquid. It comes out at a velocity that's higher. That's why it's a turbine, and at a different enthalpy. It's lost power. It's given up enthalpy in the system, and we know what those magnitudes are. And we want to know adiabatic means there's no energy loss within the system. It's completely insulated so that all the energy that comes in gets converted some way into work, which doesn't come out of the bottom end of it. And we just have to use this expression that we had before, which is this. So the expression we had before is this. Mass rate of flow, so this would be kilograms per meter cubed. These are enthalpies. We have to be mindful, and so one of the reasons perhaps I went through the effort of writing this equation out, it has to be upstream with the pump head in it to downstream. So that's why I specifically flipped it around. It matters now which direction we go from upstream to downstream. It never did until today. We could always write the downstream as number 1 and the upstream as number 2, but we have to be mindful to not do that now. It has to be the upstream has to be consistently number 1 if we're using that convention. And so in this case, this is in, this is out. This is the velocities in and out. This is the elevation. If the elevation, we can choose our datum anywhere we want, so it's probably easier to choose it here as z equals 0. Doesn't matter actually, they just cancel out, right? So, and then we realize that this is the total. You're asked for mass, the work per unit mass of the steam. So we can divide both sides through by mass flow rate. If we divide this through by mass flow rate, then this is the right term that we want. It's work per unit mass, rate of work per unit mass, and the rest is just plugging and chugging. So you have to put the right values in for these. I guess this is velocity in. It's just below here, right? 60 meters a second. This is 30 meters a second. And H2 and H1, whatever they are, they're these numbers here. So I guess this is 3308, 3348. I would tend to write that as 10 to the 3 because it was kilojoules per kilogram, and likewise write this as 2550 times 10 to the 3, and that would be in joules per kilogram. And joules per kilogram and meters squared per second squared are equivalent to each other, and then you just do the math. These are just conversions in there to get around that. So no big deal. So you just have to be mindful of the fact that you have to write things in the right order between upstream and downstream. So in this is always incoming fluid, this is the outgoing fluid, and it follows all the way through here. And the enthalpy term includes the pressures that are in the system as well, which aren't otherwise given in this. It's just given as a combined enthalpy, which is enthalpy is equal to internal energy plus pressure over density. They use little hats. I don't know why. Upside carrots, I guess. That's it. So that's so we won't use that expression very much, but we've used it once at least. So that's the linkage with some of the things maybe that you'll see in your thermo class. And the other one is to be able to look at using Bernoulli with these energy losses in the system. Energy put into the system as a pump head, and energy lost in the system by flowing through it. And the other example to do is just a pump storage scheme example, and to show exactly the form of the losses. And so you can imagine this is a pump storage scheme up in the Alleghenies or wherever else it is. You have two reservoirs linked by a turbine hole, which is usually buried in the mountainside. You can run it in either of two modes. You can run it producing power from the system by running it through, or you can run it by putting energy into the system and giving potential energy to the fluid that comes into it. And so you can look at each of those. So I guess using it in hydroelectric power mode, HEP mode. What do we do? Guess I didn't need to do such a big arrow. But so we've got Bernoulli's equation. So big reservoir assumption. Let me write just P is equal to 0. Big reservoir, I guess it's atmospheric, so the big reservoir assumption is that velocity is equal to 0. Either way, right? Because it's a big volume. So you can write Bernoulli in terms of this. So it's, what is it? It's Z1 plus no velocity term, no pressure term, plus HP equals Z2 plus head losses. Head losses are always positive. And so we can calculate the power that comes out of that from the turbine is just going to be equal to Z2 minus Z1 plus head loss. With our sign convention, Z2 is 0 and Z1 is a number bigger than 0, so this would be negative. So this is a pump. Sorry, this is a turbine. If the head losses are 0, just forget this term for now, let's assume it's 0, then by definition the energy per unit mass flowing is going to be given by this pump head, and it's a negative value, which means it's producing power. The reality is that the head losses will be by friction on this. In this mode, I guess it'd be friction pushing back up against the flow, and so this would be not necessarily equal to 0. And so if that's not equal to 0, this will always be added to a negative number, so it will always diminish the amount of power you can get out of the system. It always acts against you. I always use pulling my bag across the table. When I pull it with me, friction works against me, against that pull. If I push it back to where it was, then friction acts against me again in getting it. So it's used up work in both of those motions, and so to get it across the system. So the other option is to use it in battery mode, I guess. And so that is pump storage scheme. And all we need to do is switch it around. Just need to be mindful of our sign convention. Be the same equation up here. It's going to be Z1 plus HP equals Z2 plus HL. Again, we can rearrange it. It'll be the same equation. It's going to be equal to Z2 minus Z1 again, plus HL. And by definition, since Z1 is, did I switch them? Z2. Since Z2 is larger, then this is going to be positive. Plus VE. You understand what it is? I remember getting through to about week 10 and someone asked, what the hell does plus VE mean? It's positive, right, in this case. So this is meaning you have to apply a pump here to be able to pump against the friction as you're pushing it up the pipe. So this is up and this is down. Friction always acts against you to be able to diminish the energy in the system. So what you'd like is that this would go to zero, and I guess you can make it go to zero by doing a bigger pipe will have less friction, because you can imagine that if you're squeezing stuff quickly down a small pipe to get a given velocity, then if you make the pipe much bigger, the volume to surface area ratio is much less, and therefore there's less friction applied. But there's obviously limits to how big the pipe is, because it's more expensive to make a big pipe that goes up inside a mountain, which would be typically bored by a tunneling machine. And so that's what this example is just doing. You can see the rest of it there. So that's it. I don't know that I have much else to talk about. I didn't look at reviewing that. That's it. So just to recap, it's those are the two. We didn't go through the trauma of deriving all the thermodynamic quantities. I'm not sure that's particularly productive. But the bottom line is we have these two expressions. One where we have effects of heat in turbines and engines that we want to accommodate, and that's quite useful to look at in this way. It's still looking at basically the behavior along a streamline from upstream to downstream, and we have to write it that way. If we write Bernoulli for the case where this work here is really encompassed in this term, don't know why I wrote it that way, then this is much more convenient for most of the things we'll do in this class, is looking at losses of pipe flow in flowing in fluid circuits or in boreholes, losses when you flow around wind turbines, and of course those losses around wind turbines would be exchanging energy from the flow to the actual structure, which is turning, which is really the mechanism by which you're doing it. And I guess we'll probably see when we talk about pipe flows that what we've talked about so far is that in weeks, so it's week 8, we'll talk about ultimately in week 10 and 11, we'll talk about pipe flows with flow within here, where we have to worry about the friction losses. And these frictional losses are what we'll refer to as H sub L. If you're looking at, in week 12, we'll look at what we'll refer to as external flows, which is kind of the same system, but now our flows are doing this. But really, the essence of those flows are that they still impart some kind of force to that structure. And so if you're thinking about flow within a pipe, the friction is applied on the fluid and slows down the fluid, and that's what you're interested in. If you're looking at a wind turbine, not really a very efficient wind turbine, is that the force is applied on the blades as an external force, and it's really that transmission of the force from the circulating air onto the structure, which provides the motive force for the structure, for you to attach it to an electrical generator to be able to make power. So that's really all. That's a commonality in what we'll deal with. Okay. Okay. Good. Any questions?